Hi.
Hi.
Thank you for your talk. I was wondering about the AIMS programs, facilities.
Yes.
So it's master's degrees and
Yes.
doctorates as well.
Yes.
And you
Yes.
said it's open to anyone.
Yes.
Does that include people who are not from Africa, people from Europe, or?
Yes, it is. So I'm rather old, okay, comparatively to all the Africans involved. And so we had a very interesting discussion about exactly this point. So my prejudice when we started AIMS is Africa comes first, okay? So they're the ones who've been excluded. We need to prioritize Africans. So then we launched AMI last year. And the leader of it is not me, it's a young African, Mustafa Cisse. He's a brilliant guy, he works for Google, but he's a professor at AIMS. And he doesn't take my advice. He prefers to think for himself. And so we launched AMI, we had the funding from Facebook and Google, and we were opening the website. And by the way, do look at the website. It's an amazing example of AIMS, AMI. Oops. Oops, okay. AIMS, AMI.org. And if you look at this, you will meet Mustafa. So Mustafa, so I said, okay, we have admissions, we have 800 applicants, we have to read all these folders. You know, what should we do? Exactly your question. So of course people did apply because this is a big course, and by the way, the faculty on this course is better than the faculty in anywhere in the world. The leaders in the field, the people who wrote the textbooks, all teach on this. Look at that website. You'll see there just the best people came to teach that course. So, so people applied from Mexico, Brazil, and I said, oh, you know, we should prioritize Africans. Mustafa said, no way. He said, we're doing this for the world. We're doing this because we truly believe that Africa needs to be world leading in science. That means openness. So, and you think how much we will gain if a Mexican comes and they interact and they learn to love Africa. They're now an ambassador for Africa, right? So he overruled me, and so yes, AMI is open to anyone from anywhere. And our goal is to make the very best course in the world, which will be the envy of the whole planet.
Thank you very much.
Thank you. That's true. That's true. By the way, there's a number of ways to get involved with AIMS, one of which is to apply to be a tutor. So we have, as well as the 50 students, we have resident tutors. So for people who have their PhD, or maybe postdoc, and they want to spend a year or even 2 years in Africa among this community of students, helping the lecturers teach. Every AIMS center has between 6 and 8 such fellows there. So there are lots of ways to get involved.
First, thank you very much for this fantastic presentation.
Thank you.
I was coming for the question of Africa. I can even tell that 45 years ago, I was teacher of mathematics and physics at less than 30 miles from Ishango.
Wow.
In Congo. So, but I will have my discussion about Africa with a professor of UCL on Friday. My question is more about your cosmology.
Okay.
When I see the universe,
Yes.
you show, I don't know how I call it, like a glass, you show the Earth in the middle. Do we have to consider each point of the universe is in the middle somewhere?
Great question. So this is one of the sort of paradoxes, and it's a paradox which became even more strong recently. Okay, so the paradox is, when we look around, we appear to be in the center of the universe, right? Because as we look out, it gets younger and younger, right? However, the statistics, you know, so basically you can look at distant regions, correct for the fact that you are seeing them earlier, and ask them, are they really different than what we see in our vicinity? The answer is statistically they appear the same. Okay, so the conventional viewpoint is that it appears the universe is consistent with the homogeneous, meaning the same everywhere, homogeneous initial universe coming out of the Big Bang, and statistically the same everywhere. There's no evidence for a center. However, that's the traditional viewpoint. The discovery of dark energy changes this a little bit. The reason is that this acceleration due to dark energy means that very distant objects are being pushed away from us extremely fast. So fast that we will never, ever see them. Okay, so that's strange, but it turns out to be true that in Einstein's theory of gravity, it is possible for space to expand so fast that even light cannot cross it. The consequence of that is that our observable universe, observable, even in principle, became finite. We will never see much more than this patch. If we follow ourselves to the infinite future, we will see about 25% more than we can see now, and that's it. So the universe became finite, and we are in the middle of the finite region we can observe. Now, in the classical picture of a homogeneous universe, you say, oh, maybe it's infinite, it goes on forever. But should you say that when you can never, ever, even in principle, see it? Is it meaningful to talk about an infinite universe when you can never, no matter how long you wait, you can never experience it? I suspect probably not. Okay, but then we need to develop a new conception of what it means for us to be in the middle. You see, we really are in the middle in a number of senses. We're in the middle in space of the region we see. We're in the middle in time because there's some very uninhabitable future with only dark energy and the Big Bang in the past. We're in the middle in scale. Okay, so if you take the ultimate size of the universe that we can see, it's finite. That's a definite length scale. That's the greatest possible object we will ever see, according to Einstein's theory of gravity. That's a length scale. It's about 20 billion light years. Take that scale as the biggest scale you would see. The Planck scale is the smallest scale you could see. It's a scale so tiny that if I built a microscope to see it, all I would do is make a black hole, because the light would have to be very short wavelength, and that means very high energy. And as I focus it on my object, the object would collapse into a black hole. So there's the smallest possible scale. It's called the Planck length. It's 10 to minus 43 seconds, basically, is that scale. Smallest visible scale, according to gravity, largest visible scale. Take the geometric mean, halfway. That's the size of a living cell. Okay, so we are literally in between the two extremes. And by the way, Lemaitre's successor was Teilhard de Chardin, also Belgian. He speculated exactly along these lines, without mathematics, but he thought life somehow represents the leading edge of the universe, and it does, because the most complex things we know of in the universe are us, and we are bang in the middle between the tiniest and the largest things possible. So what that means, we don't yet have a physical picture or theory which accounts for this middleness, but I strongly suspect that will be the future cosmology. The universe is probably not infinite, because we can never see it, so it's a finite object, and somehow, in some sense, we're in the middle of it. So we are in the center of the universe. I'm only for the universe.
Hi, I'm not a scientist. I studied politics, so but the statue.
More important things.
No. But the statue that's outside of
Yes.
Georges Lemaitre, it
Yes.
says below, that he discovered the day that didn't have any yesterday.
Right.
But when you show your representation of a
Right.
butterfly,
Right.
and then you see that what you describe as the Big Bang is in the middle,
Yes.
but then it does have a yesterday because there's something happening before.
No. That's a wonderful question.
And that's from
It's a wonderful
somebody who doesn't
question.
understand anything about cosmology. It's,
Yes, it's a wonderful question, but it's exactly what Stuckelberg answered. So you have this particle, you see this is time, the vertical scale. Here's a particle, I follow it back in time, this axis, and it doesn't exist before this time. There's no particle down here. It only exists here. So the day before yesterday is up here. Okay? So the answer is, if this is today, there's not just one particle, there's its partner. Okay, but it's actually going backwards in time in order to create this particle.
I'll still be thinking about it in my shower.
Yes. By the way, this scenario for the universe is absolutely compatible with the philosophy of somebody called Spinoza. So Spinoza was a very foundational thinker, and one of the questions he focused on is causality. What does it mean for something to cause something else? And so his concept of the universe was that it is the object which causa sui. It caused itself. I don't really understand his reasoning, okay, but this definitely realizes that philosophy, that literally one side of the universe caused the other. But you see, to answer let's go to the other picture. You can say in one picture, the day before yesterday was here, right? But the problem is time actually goes this way in this part of the universe. I mean, here it's dense. So it's all a matter of perspective. According to us, we would say a universe collapsed to create us. But there's a completely equivalent picture, which is that we collapsed to create this expanding one. And they're equivalent. Okay, so you avoid the paradox. Or at least sidestep it, not completely avoid.
I would like to come back to the aims. How do you cope with the problem of language barriers? Africa is diverse in languages, with Francophone, Lusophone, Arab blocks.
Absolutely.
So how do you
Wonderful
make a
question.
kind of equilibrium in attracting
Wonderful
these people?
question.
And the second part of my question, how do you make sure that the people, these brilliant people that you train,
Right.
will serve Africa and
Right.
not disappear in the developed world?
Lovely. So great questions. So the first question, what do we do about language? We're very fortunate. Mathematics is a universal language. So, 2 + 2 = 4 in all known languages. And so since we are primarily teaching maths and science, immediately the students have a common language. Okay. Now what we actually do is we ask all of our students to take language programs before they come to AIMS, so they're at least bilingual. I mean, well, some AIMS centers have French and English courses, Cameroon and Senegal in particular. The other ones are Anglophone anyway, and pretty much all courses are in English in Ghana, South Africa, and Rwanda. Rwanda was Francophone, as you know, but they abolished French, and they made English the national language, so all teaching in Rwanda pretty much is in English. But the real answer is that the African students are so determined to study, they're quite happy to overcome the language barrier. So I went to AIMS Senegal, for example, it was 2 or 3 years ago, and I arrived at the center, I met a student, bonjour, comment ça va? and we had a little conversation in French. He had a very good accent, much better than me. And after some minutes, I asked him, "Oh, where are you from?" And he said, "Nigeria." So it's a barrier, but it is not the same as it would be outside Africa. Many African students, it's quite normal for them to speak 3, 4, 5 languages, and to ask them to learn English, in the case of Francophone students, not a big problem. So in practice, we find it's not a big problem. We have language teacher at the program. They give courses in how to, it's not just language, it's how to write a scientific paper. See, most programs in physics never teach physicists how to express themselves. That's why physicists are generally very bad, and mathematicians even worse. Okay? So, but the whole point of AIMS is to do it better than anywhere else in the world. So we have a language teacher, and every week the students get classes in how to give lectures yourself and how to write scientific papers. And this language barrier is usually only a problem for 1 or 2 students out of 50. You know, some of them happen not to be very good at adapting, and then they struggle. But by the end of 10 months, they're beginning to be fine. The internet has also helped enormously. The other question is, how do you make sure that the students, after this doorway you opened, right? We open a door, they can do PhDs and all that. How do we make sure they stay in Africa? And the answer there is that we give them their best life experience in Africa. When they're in AIMS for 10 months, they're surrounded by their comrades who have experienced similar troubles, right? They have the best lecturers come to teach them. There's a very exciting atmosphere. It's not a torture. It's fun. I mean, it's very hard work, but it's fun. Usually when they go overseas for PhDs, they're very disappointed. Okay? If you go, certainly you go to Canada, it's very cold, and the food is terrible. Okay? And you know, so instead of going overseas and getting the impression you can only do science in the West, all right, or outside Africa. That's the normal situation. African student goes overseas and then everything is different. They think, oh, you can only do science there. Instead of that, we give them the best experience in Africa, and then their hearts remain in Africa. Okay, so the evidence is about of the AIMS alumni who are employed, and that is currently about 49% are in employment, so permanent positions. Does not include people doing PhDs, which is another 25%, and masters is another 15%. So of the employed ones, half of them, 80% are employed in Africa.
C'est une toute petite question en français,
Oui,
dans le
c'est bien.
prolongement de ce
Merci.
qui vient d'être dit.
Okay.
Dans les étudiants du réseau, est-ce que les femmes sont intéressées, sont présentes?
Merci beaucoup pour cette question. Oui, from the beginning, AIMS' objective is to open access to people who have been denied access. And that includes Africans, but especially women. So women are denied access to physics and mathematics worldwide. It's a disgrace. At senior level in physics and mathematics, less than 10% of professors are female. So when we started AIMS, we made as our objective that the student body must be diverse, geographically, culturally, gender-wise, with a minimum of 30% women. So that was our objective. We believed that 30% would justify itself because, and I should say we're never rigid, okay? So the 30% doesn't quite capture it. It's a goal, But rather we prefer, when we see an application, we prefer to look for the potential of a student, which means you must compensate. If they come from a background which is disadvantaged, and one of the factors is being a woman, that is inevitably a disadvantage, you must try to estimate how well could they do in the right conditions. So factors like motivation, determination, strength, right? They come into it. And when you interview them, you must judge those characters. So from the beginning, we took 30% women. It turns out the women, when they arrive, are usually quite shy. Most of them have never left home. They've never left their country. They, men are more arrogant and generally. And so the women arrive, they're quite shy. Then the whole environment is designed to be super safe, supportive. It's great for them to be away from their families because then they don't have all those pressures of having to support the rest of the family. So for the first time in their lives, they can focus 24/7 on improving their mind. By graduation, the graduation speakers who are women are always the best. So during 10 months, those women really grow as confident young scientists who can express themselves, and they almost universally, they give the most interesting graduation lectures. So that's been one of the big successes of AIMS. It's not an accident. 2 of our alumni are women who are here. And we very much believe, if I was to make a picture of the next Einstein, it would be a woman. I'm happy, yes.
Thank you, Neil. It was a very, very nice presentation.
Thank you.
And I have a question about the Master in Machine Intelligence.
Yes, Ami.
Is there any philosophical consideration in this Master?
Yes.
Because I'm thinking about 2 questions.
Yes.
The first is, what will happen when these machines will be more intelligent than we are? And I think we are arriving there.
No.
No?
Don't worry.
And the second question is, how about sustainable development? How we will feed these machines?
Right. Wonderful questions. So the founder of AMI is Mustafa Cissé. I mentioned him before. So he's a young Senegalese. He came from a peasant family in Senegal, in the rural area. His parents never went to primary school. But his parents moved to Dakar to fund their children to go to primary school. Okay, so he loves his parents very deeply. They gave him his chance. He went to University of Cheikh Anta Diop. Actually, he was the student leader, president of the students at his university. And he met the president of the country to negotiate. So he's quite an interesting individual. So why did Mustafa achieve such prominence in this field? He was appointed by Facebook, and now he is a scientist at Google, the director of the first Google Research Center in Africa. Right? There's none in South Africa, Egypt, Nigeria. No. He in Ghana. Why? The reason is because Mustafa made his name in science within Google by pointing out the bias in search engines, in all of their software. The software was written in California. It was not designed, it was written by people who had no concept of bias. So he both mathematically, statistically, sociologically showed them your algorithms are hopelessly biased against a large fraction of the world's population. And he completely convinced them. He went to California, he met the CEO of Google. They said, you have to work for us and fix the problem. And so Mustafa said to them, the only way to fix the problem is to have engineers and scientists who come from that region. They will be immediately aware of bias, okay? So that is his field. And that is the mission of the whole program. Actually, as far as Facebook and Google are concerned, they hope to hire all the graduates to work for them and fix their biases. Okay, that's the main objective. So indeed, the whole field of AI has philosophical implications, very profound, and it's very dangerous. And Stephen Hawking, is famous for a few years ago coming out and saying AI is the big danger, and it's true. It is very, very powerful, and like all powerful technologies, like nuclear physics, it can be very dangerous if abused. Now, having said that, so if in a practical question, it is essential we control machine learning and AI, we try to eliminate biases, we try to use them in safe ways. They're very powerful and very dangerous. So, myself, I'm very nervous in a self-driving car, and I think that's correct. One should be nervous. However, if you ask the philosophical question, are they really intelligent? Do they really learn? This name, machine learning, it implies machines can learn. Artificial intelligence, it implies a machine can be intelligent. I don't believe that's correct. What machines are, the whole field is really automation. It's neither learning nor intelligence. It's automation of tasks we know how to perform. Okay, it's just automation, but it sounds more fancy if you call it learning and intelligence. But this was summed up best for me by the chess player Garry Kasparov. So he's an expert in artificial intelligence. Why? Because he is the first person to be made unemployed by artificial intelligence, because he played chess and then IBM Deep Blue defeated him comprehensively and he gave up chess. Okay. So Garry Kasparov draws a very nice distinction between decisions which machines are capable of making. So a decision, you calculate all the inputs and you say, under this circumstance, I would make the following decision. There's one thing with decisions, and machines, you can automate a decision. It may be dangerous, but you can do it. But there's another thing, which is choice. Human beings, we usually govern our lives by choices, not decisions. Right? We're faced with some logical argument, you should take this job, you should move here, you should work 15 hours a day, and there's a logical thing to do, and there's the thing you choose to do, and they're very different. So we make choices based on our intuition, which we don't understand, okay? And most of what we decide is pretty irrational, okay? So Kasparov says there's this choice. Machines can do decisions, fine, but they can never make choices. And I think it's a nice way of crystallizing. So for me, that gives me some comfort that I'm not going to be replaced by a machine.
My question is about the 4.5 parameters for the universe.
Thank you.
Because I didn't see a fundamental constant like Planck's constant and the speed of light. So I wonder if it's deduced by those 4.5?
That is summarized by the word standard model.
Okay.
The standard model includes all the laws of physics with those parameters. Okay. So it's just that, we built the standard model to describe physics in the laboratory on Earth. Newton's constant, speed of light, all of these things are tested on Earth in experiments. That's what I mean by a standard model. So everything in the standard model was understood through experiments on Earth. Now we take those laws on Earth and we apply them to the whole universe. And what do you know? They work. They work. But you have to add 4.5 extra numbers. Dark energy, dark matter, we can't detect them on Earth. We can only detect them using the cosmos. And why there's more matter than antimatter, that seems to be something that happened at the Big Bang, not on Earth. It's too difficult to test on Earth. and these variations in the density. There's nothing we can do in a laboratory on Earth to understand where they came from. They came from the universe. So it's just the extra numbers beyond physics known from the Earth. But isn't that amazing that you go 14 billion light years and you only need 4 more numbers? It's amazing. There's no multiverse.
At the Big Bang, instead of starting from a point,
Yes.
Could we start from an infinite array of unlocalized waves?
Infinite array of?
An unlocalized array of waves.
Unlocalized array of waves. Yeah, no, that's fine. I mean, if you have some definite ideas, put it in mathematics. That's the basic rule. You have to put your theory into mathematics to make sure it is logical, and then it should make predictions, and then we test it with experiment. So everybody can play this game. Yes. Please feel free to leave if you have something to do. I'll have a drink.
Hey, I was curious if you said before that we are in many ways in the center of the universe.
Yes.
Do you therefore think that it is unlikely that there is life somewhere else in the universe? Because
Oh, wonderful question.
will then not be at the center?
Yeah, so the odds just went down. Because of the existence of dark energy, the universe, the observable universe, became finite. So people used to say, if the universe is infinite, surely there must be life somewhere else. Okay? And now that is a bit problematic, because if the universe is infinite, there must be a probability of yourself being somewhere else. Okay, infinite universe, everything that can happen must happen, and it must happen an infinite number of times. So if you are there now, there must be infinitely many copies of you. I mean, infinity is a big place. So that's a bit strange. So you could almost say, if the universe was infinite, you can say, there must be life somewhere else, because at the least there's me, and there must be a copy of me, because I had some finite probability to be formed. Whereas if the universe is finite, it's not necessary. There may be only life in one place. So, yeah, which is it? I don't know. But it is a bit of a mystery that we haven't seen any evidence for life. I think we would. For example, if there was more advanced life than us, and we looked a long way away, over a big volume, we should see some engineering. I mean, this advanced form of life should be able to manipulate stars and create advertising signs, and and we don't see any. Okay? We see the laws of physics operating without any exception. We see no sign of intelligent life. So to my mind, it is perfectly possible that there is no other life. It means we are even more precious. It means we have to protect this planet. We have to look after ourselves, because what awaits us is enormous. And we're the leading edge of the universe. These are actually the words of Teilhard de Chardin. I recommend it strongly. He was a visionary. He didn't do any physics really, but he had somehow a vision of the universe, even before the Big Bang theory and observations, where he in some ways anticipated how he thought it might work. So And he said, we are the leading edge of the evolution of the universe. I think we should see ourselves that way. Of course, makes us more important. But that may be a good thing, because we should realize, every one of us is very, very important. There's another fact you may be entertained by. 14 billion light years seems a long way away. So if the universe is that big, does it really matter? Because we can't go there, right? It's so far. Would it take us 14 billion years to get there? Now the answer is amazing. And this is in a book by Carl Sagan, who did the Cosmos series. And so Carl asked himself, if you have a spaceship where human beings could survive, and it accelerates at 1g, just the same as we feel in this room, but it's in space, so it's accelerating at 1g, how long would it take you to, in your own time, to cross the universe? Okay, so naively you might say 14 billion years, because even if you go at the speed of light, but you have to think about relativity. In relativity, when you travel fast, distances shrink. Okay, that's called Lorentz contraction. And so it turns out if I travel at 1g for 23 years, I'm on the other side of the universe. So within a human lifetime, this is a pretty fancy rocket ship that can go at 1g for 23 years, right? I mean, we have to think about the fuel and all of that. But if you can do that, you can cross the universe in 23 years. It's amazing. So suddenly you realize this whole universe is not just finite, it's accessible. And then it's our responsibility. It's like our garden. But let's not spoil the earth. Okay? Because we need to explore the garden.
So I have another question. Before, the universe used to be seen as infinite, so there was no point in thinking what's beyond.
Right.
But now that we think about it as being finite,
right.
Do you have any ideas what might be beyond the universe, the
Well,
borders?
so we think it's quantum. Okay, so because of these variations, they have the character of quantum statistics. So if it's quantum, one has to be very careful in quantum mechanics not to speak about things which are not testable. For example, when an electron lives in an atom, people used to think it's like a planet going around the sun, and the electron has some. But Heisenberg showed this is completely wrong. There's the uncertainty principle. So if you know where the electron is, you cannot know how fast it is going, and it's pointless to ask. It's just it's unknowable. My strong suspicion is questions like that one don't actually make sense. When we ask what is beyond what we can see, ever, probably doesn't make any sense. We don't know how to quite justify that, but Heisenberg was quite hard to justify, still very hard to justify. When things become quantum, our classical language is not applicable.
But that's with our understanding today.
Yes.
In 100 years.
Right.
In the day where we could build that rocket that can cross the universe.
Right.
It would become sensible to start thinking, so now that we've crossed the universe, can we go further? What's next?
Yes. So these arguments in principle mean that even if I cross the universe, I cannot see further. So they're very, very strong, right? So I can build a spaceship to go at 1g for 23 years. I can go to the other side of the universe. What I will find is I can never, ever, ever see what's beyond it, according to the known laws of physics. So they're very strong limitations. There's no way around. So in order to break that limitation, you would have to break relativity or quantum mechanics, or both. And that's, in my view, unlikely. because they seem to work very, very well. So.
And I have a last question, I'm really
Sure.
sorry. You didn't say anything about black holes in your
Right.
presentation, so I was wondering
Right.
what your take is on what might be beyond, well, inside of a black hole.
So I do have a strong opinion about black holes. Black holes, of course, are Hawking's speciality. He proved, at least Roger Penrose and Hawking proved theorems about black holes. They are unavoidable. They do exist. We see them now frequently. In fact, in the next 2 months, some pictures will be revealed of the black hole in the Milky Way. So just look out for it. I'm fortunate, I've seen the picture already. There is a black hole in the Milky Way, and we can even see it. Okay, so basically there's a plasma which is hot, and you look at the plasma, you see a dark patch, spherical. It's this plasma is orbiting the black hole, and the black hole is blocking out the light. So there is a black hole. We can now see it in the Milky Way. The paradox of the black hole is, what happens to things that come inside, fall inside. Classically, they can never escape. But quantum mechanically, as Hawking showed, just like the particle turning around in time, a particle inside the black hole can actually leave due to quantum effects, and he calculated those effects. This created all kinds of paradoxes. So the world of theoretical physics for the last 30 years has been puzzling about black holes. Nobody has a good picture. My explanation of that is that, you see, the black hole is a classical concept. It's a geometry of space-time which is curved so that light cannot escape. That's completely classical. That is not the correct picture of quantum geometry. We actually know how to do quantum calculations, but they're very difficult, because what it means is that space and time are quantum, so they are fluctuating. So the horizon of a black hole is not a strict surface in space-time, it's fluctuating. There is a way to calculate. It's very difficult, and nobody so far has done it. But I actually believe we are developing techniques that within 10 years or so will unambiguously answer how to describe black holes. But the resolution of all these paradoxes is that space-time is quantum.
Thank you.
Thank you. I'm a theologian. I am out of my comfort zone. Thank you for bringing up Spinoza, at least I know him, and Teilhard de Chardin.
Okay.
My question is twofold, and it concerns my discipline, so maybe you're out of your comfort zone now. Where is God in a symmetric universe? That is the easy question.
Right.
And does the issue ever come up with your students in Ames?
Yes.
As I understand,
Yes.
Africa is still maybe more than we're here in Belgium,
more religious.
attached to
Absolutely.
religion. Yeah.
Great question. So it's ironic that the founder of modern cosmology was a theologian, Georges Lemaitre, and he had the perfect answer to this question. I'll just quote him. He said, "When I was very young, I learned that there are two paths to the truth, spiritual and scientific. And I decided to follow both." And he did. And he did. And he saw no contradiction, and nor do I see any contradiction. Because especially if the universe creates itself, the idea that the Big Bang was the beginning, in a sense, and this is a paradox, goes away. You still have to explain why it's there. Why is the universe there? Right? It's a kind of physical object which emerges in this way. You have to explain why the laws of physics hold, why, all the questions which physics cannot address have to be answered, and physics is simply incapable of answering. So for me, it's never been, the Big Bang was never a disproof of religion. That's kind of ridiculous. People misinterpreted it, or a proof, I should say. I mean, the Pope, in fact, said, oh, great, there was a Big Bang. That means God made the Big Bang. But, that doesn't answer any scientific question. Okay, so I think religion shouldn't attempt to be science, and I think science shouldn't attempt to be religion. And they're both forms of human searching. Yeah. The second question, in Africa, indeed, most of the students are religious, and we have a number of religions. We have fundamental Christians, we have fundamental Muslims, we have all belief systems. We have many students actually believe in their own, traditional belief systems involving ancestors and spirits. Okay, this is quite common, and so we tend to discuss these things, and it's very interesting. In the early days of AIMS, in fact, there was some hostility that could arise, and one of our worries was that the Muslim students, let's say from Sudan, may not be comfortable with the Nigerian students, because there's religious conflict in Nigeria, Christians and Muslims. We were worried about it. And for the first couple of years in South Africa, indeed, there were some situations. For example, we had a Nigerian student who was a deep Christian, and he put on the back of his shirt a message, repent, let Jesus into your heart, and insisted on sitting in the front of the lecture with this sign so that all the non-Christians would read it. And, we had to reason with him and say this isn't. So then what happened is the Muslim students celebrated Ramadan in the Institute, and every night they would invite 2 of the non-Muslim students to dine with them and to learn what is Ramadan about, what are Muslim beliefs, and so on. And in this way it became normal. And so actually this is a wonderful thing, that in AIMS centers the diversity is not a source of friction. And most of it is cultural precedent and history. Everybody knows that it's just normal. When you come to AIMS, there's multiple religions and languages and beliefs. That's fine. So that it is a model for how the rest of us should behave. But it is, I think you will confirm that, people's fears that creating the melting pot in Africa, would create friction is not realized at all. You have students from Congo working with students from Egypt and Madagascar, and this is completely natural. And that thing is, in fact, I would say, the greatest success of AIMS. This bridging. And I believe that science and mathematics are the optimum tool, simply because they are culturally neutral. At least mathematics is more culturally neutral than any other field of human endeavor. Maybe, excepting music and sport and so on. But academic mathematics is pretty neutral. And so it's a good way to bring people together and then engage in some activity which is common.